Hi everyone, this is worksheet 6.3, and so hopefully you have a blank sheet of paper in front of you because that's what we're going to be using for this worksheet. We'll just start from totally blank this time. So let me go ahead and write that down here. This is worksheet 6.3, and make sure that you put your name at the top of your worksheet. And the subject today is going to be the entropy and free energy of mixing. Okay, so I paused for a moment and drew this lattice, which is going to be what we're performing our calculations on. Let's call all of these circles, which represent particles, particle A over here on this side. We can call these darkened ones particle B. And even though there's 9 spaces on each side, we're going to say that there are, we're going to generalize this and say that there are NA spaces on this side and NB spaces here on this side. There are also NA particles on this side and NB particles on this side too. And so this is a completely unmixed system. All of the different particles are separated by some sort of barrier right here in the middle, and they've not been allowed to mix yet. And I just want to point out that this model is probably closer to a liquid or a crystal than an actual gas, but nevertheless, the model is going to work. All right, we've been talking about ways to arrange the system, and hopefully you see that there is only one way to arrange the system like this, because without mixing it, so for the unmixed, or we might say the pure system, where each component is pure, as long as we keep it pure, we keep the particle on the correct side of that barrier in the middle, exchanging any two particles just results in exactly the same configuration. And so hopefully you see that what that means is that big W, which represents the number of ways to arrange a system, so we can say big W pure just equals 1. And if we use the Boltzmann entropy formula, KB log W, that implies that the entropy of this pure unmixed system is 0. So when we find out what is the entropy of the mixed system, that's going to be our delta S of mixing, since for the system to be completely unmixed, the entropy is already at 0. All right, so if we remove the partition, we'll let the system mix. And so I'm going to pause here in a second and draw that. Okay, so now we've went ahead and mixed up our system. As you can see, that partition's been removed, and now there are roughly equal numbers of particles on each side of that partition, and because of thermal energy, they're moving around and exchanging places, and the system's getting all mixed up. I'm going to say that there are NA plus NB equals N total number of spots now that these particle A's and particle B's can inhabit. All right, and so you can think about it for a while to make sure that it makes sense to you, but the total number of ways to arrange this system are what's called a binomial distribution. And the binomial distribution looks like this. There's going to be NA plus NB up on top of a fraction, factorial, divided by NA factorial times NB factorial. What this just means is how many ways are there to arrange two types of objects in a certain number of places, where here are the two objects and here are the number of places up here that the system can be arranged as. So then log big W in this case becomes the log of NA plus NB factorial divided by NA factorial NB factorial. Okay, and now we can use the rules of logland and spread out this division and this multiplication there. So that's going to be our next step. Log NA plus NB factorial minus log NA factorial minus log NB factorial. All right, and now this is our chance to first of all indicate that that's n, and so we'll just be using n from now on instead of NA plus NB. But now we can also use Stirling's approximation, which if you recall from class, tells us what's the log of a factorial. And it says that the natural log of n factorial, whatever n is equal to n log n minus n. All right, so everywhere that we see a log factorial, we're going to replace it with Stirling's approximation. And it's going to get a little bit long here, but remember we're calculating the log of big W. So we're using n, no longer NA plus NB, log n minus n. So that's from this expression right up here. And then we've got minus NA log NA minus NA. That's from this expression here. And then we've also got NB log NB minus NB. And that's from this expression right up here. Now, the next step is going to be to distribute these negative signs and also to use the additions and subtractions here and just kind of move things around a little bit. So I'll do that first step, n log n minus NA log NA minus NA, or that's a plus NA because that negative got distributed, minus NB log NB plus NB. Okay, now this whole thing equals n log n minus NA log NA minus NB log NB, and then I bring those single terms over here at the end, plus NA plus NB, but this right here just equals positive n, so those cancel out, and I'm left with just the logs. Okay, the next step is to split this n into NA plus NB. So let's go ahead and write that out next. We get NA log n plus NB log n minus NA log NA minus NB log NB. Okay, now we can group together these NAs and group together these NBs. So let's do that next. We got NA times log n minus log NA, and then we've got plus NB log n minus log NB. Cool. Now we're going to use the rules of logland for these subtractions here and turn those into divisions. So we get NA log n over NA plus NB log n over NB. Okay. Now what we can do is flip these around here inside the logs and add a negative sign. And remember, one way to think about that is if we put a negative sign out here, then that is like multiplying the log times -1, and a multiplication on the outside of the log means an exponent on the inside of the log. So that's like doing this to the -1 power. Minus NB log N over NB to the -1 power. And this just equals negative NA log NA over N minus NB log NB over N. And if any step in this process doesn't make sense, go ahead and pause it and give it a try yourself. Okay, the next step's a little tricky, and it involves pulling out a -n out of everything. And so I'm going to write it out, and then you can algebraically verify that it's correct. Pulling a -n out of there, and I'm left with NA over N log NA over N plus NB over N log NB over N. Again, if that doesn't make sense why that's true, then see if you can algebraically verify it. You would cross out these n's here, and you would get this expression up here, right at that spot. Okay, the next step involves recognizing that the mole fraction of A is equal to the number of molecules of A over the total number of molecules, and the mole fraction of B equals NB divided by the total number of molecules. That's the definition of the mole fraction. So we're going to put the x's in wherever we can. So therefore, remember, this is still log big W, and it equals, let me erase that, this equals -n xa log xa plus xb log xb. And now we're ready to write down our entropy. So the entropy of our mixed system is equal to Boltzmann's constant log big W, which just equals negative NKB times the mole fraction of A log mole fraction of A plus mole fraction of B log mole fraction of B. And N, the number of particles, is equal to the number of moles times Avogadro's number. So remember, this is number moles, and this here is number particles. And recall back earlier in class, I told you that KB is equal to R divided by Avogadro's number. Then we can say that N times KB is equal to N times Avo's number times R divided by Avo's number. The Avo's numbers cancel out, and this just equals NR. So therefore, the entropy of the mixed system is equal to negative NR times the mole fraction of A log mole fraction of A plus mole fraction of B log mole fraction of B. And the delta S of mixing is going to be equal to the S of the mixed system minus the S of the pure system. And since the S of the pure system was just 0, this equals this expression right here. And if you look in the book, that's what it will tell you it is. So we got the same result that the book did just by using statistical arguments. All right, and then the next step is to get the free energy of mixing. And remember, the free energy is equal to delta H minus T delta S. And in an ideal gas, the particles do not interact, so there's no potential energy. So therefore, the enthalpy of mixing equals 0. And that's just for an ideal gas. So therefore, delta G of mixing equals negative T times delta S of mixing. And that means that this equals positive nRT times XA log XA plus XB log XB. And if we were to try this out with more than just two types of particles, then we could say that the delta G of mixing would equal nRT times a great big summation over all the species in the system, the mole fraction of that species times the log of that mole fraction. And lastly, I just want to show you what that looks like. I'm going to have a plot here, where down here I have the mole fraction of one of the components, say it's A. If I've got 0, then that means it's purely other stuff. There is no A whatsoever. But if the mole fraction is 1, that means everything is A. And if I were to draw the delta S of mixing, then the lowest amount of entropy is here at the endpoints, and that entropy is equal. And it sort of makes a curve that looks like this, that reaches a maximum right in the middle, where the components have equal concentrations. But if I were to draw a plot of the delta G of mixing, then this curve is actually inverted, and it's greatest at the endpoints and lowest in the middle. And that should make sense, because remember, spontaneity is determined by whatever has the lowest, or whatever has a negative delta G, and the most likely outcome is the one that has the lowest delta G of all. So the most likely state of the gas is to be in the mixed state, not in the pure state.